All right, thank you. So I am Bettens. I am a blockchain security engineer at Chain Security. And as a result of that, I am contractually obligated to tell you a story. So that happens at the other ETH, which is over there in my back. And a long time ago, some guy said to another guy, the chain is not going to secure itself. And the other guy said, we need to do something about it. And then one thing led to another, and now chain security is here. Now, having said that, I will take you to the other ETH, which is in Lausanne, with this campus. And what happens is I did my master thesis at EPFL Lausanne, called Optimizing Commit and Review for Smart Contracts, and that's the project I'm going to talk about. So what is, unfortunately. Yeah, I went to the first slide. Unfortunately, technical issues. So I exited this one, but yeah.
Yeah, I know. I'm sorry. You really don't have two presentations.
Okay, sorry about that. Okay. So, EPFL Lausanne, I did my master thesis titled Optimizing Commit and Review for Smart Contracts. And to explain that, I like to start with the title. What do we mean by commit and reveal? A commit and reveal protocol is a cryptographic protocol that looks a lot like a voting envelope, like these ones. Why do we use the voting envelope and what do we get out of them? We get two things. Because I will vote, and I don't want other people to see inside the envelope because it's a secret ballot vote. But they also need to be able to take and move around the representation of my vote. So we use these voting envelopes. And if we think of a cryptographic scheme, we would have two operations: commit, which is when you make a commitment to an arbitrary message like your vote and put it in an envelope, and reveal, which is when you open the envelope and you give cryptographic proof that the message inside was the one you originally put in. We want two security properties out of this: the hiding property, which is the fact that the envelope does not leak the information inside, it's opaque, and the binding property, which is that you cannot change your mind about your vote in the middle of things. Now, how do smart contracts use commit and reveal today? I will give you two examples relatively quickly. The first one is ENS. If you've seen the screen, what you do is you do a first transaction, which has a commitment inside, and then you wait a little bit, and then you give a transaction which opens the commitment to show the name that you wanted to reserve. And this is to protect you against front-running on ENS. The other example is, again, ENS, the ENS auction, when in 2017, I think all the names went up. They had a sealed bid auction to price the names and attribute the names. And again, they used commit and reveal, a first phase where people could commit to their bid on chain, and then a second phase where people could reveal their bids. And it's again using the same two properties to make it work in a fair and efficient way. Now, there are limitations if you study these protocols to doing it in smart contracts. The first one is that it requires two transactions always and a waiting period in between. And it increases code complexity because you have to keep track of everything in a custom way. And you need to find a way to handle unrevealed inputs. This particular problem doesn't have really a good solution because if someone doesn't open their envelope and they're the only one who can open it, maybe you ignore them, but that changes the result. But if you wait for them, you get denial of service. One thing that people do is they require people to put up collateral to ensure good behavior, but that's not capital efficient. And there's also a timing game in that the last person to open their commitment has the most information to decide if they want to withhold their commitment or not. This is an inevitable issue that you have with these types of protocol. So at the Dedis lab at EPFL, people said, there must be a better way. And that's the motivation for the Optimizing Commit and Reveal project. Now, to talk to you a little bit about the design, I will show you the normal way that a blockchain is usually structured. You will have, usually users who will produce signed and clear text transactions and give them to the consensus group, which is the way we abstract over either miners, validators, or a sequencer. And then the consensus group will produce the canonical ordering of all the transactions submitted to the blockchain. And then when you have the canonical ordering, you can execute all the transactions and get the state of the blockchain. The important thing is that transactions can already be simulated before the consensus group even does its work, and that's where a lot of MEV, for example, comes from. Now, in a Dawn blockchain, which is our proposal, instead we will have users produce an encrypted representation of their transactions and give that to the consensus group, and the consensus group will order that. Then, once they've produced the canonical ordering and they can't change their mind, another group called the Secret Management Committee, which is usually a threshold network, will decrypt the transaction and allow everyone to execute the transactions and recover the state of the blockchain. Now, what applications are we helping with this? We have a theoretical model for what we're looking for. We're looking for applications where there is a state of the application and there's some logic for updating the state. So the logic can look at the current state and it can look at multiple people's inputs to produce the next state of the application. If you want an example, in the case of the auction, the state would be the state of the blockchain, the inputs would be all the bids, and then what you do is you look who has the highest bid and you give them the object of the auction. Now, what security properties do we need? We want causality, which is the property that nobody can alter the state of the application after seeing someone else's input, and that is against front-running in particular. And we have the fairness property, which is that no participant can cancel or change the input to the application after seeing anyone else's input. Now, the research goal we set out to do is to implement temporary encryption with delayed execution, which is another name for our proposal on a smart contract blockchain. The expected benefits of such an approach is, first of all, complete front-running protection. We also would have higher credible neutrality because the consensus group would not be able to arbitrarily make decisions based on transactions because they're encrypted. And we want to show that we can implement efficient and safe sealed bid auctions on top of the new system. Now, should you do this on an L1 or an L2, we are agnostic with regards to this. They can both have benefits. So we also implemented 3 variants of the scheme. I will skip the last one, but I will describe threshold public key encryption, which is a system where transactions are each encrypted independently, and the SMC is able to decrypt any transaction individually. So the SMC is expected to decrypt every finalized transaction one by one. And the other mode is called threshold identity-based encryption. In this scheme, transactions are encrypted such that they can be all decrypted if they have the same block number. And the SMC will look for a finalized block with the block number, but it's unable to decide individual transactions. It has to reveal a decryption key for every transaction that was encrypted for that block number. Now, talking a little bit about the implementation, what we did is we took an Ethereum blockchain, we took Go Ethereum, and we added functionality for potential hard fork that would add the new rules and the new functionality. The application that we run is a sealed bid auction for one NFT, and we want to simulate at least 1,000 bidders to show that, that it scales. And it's a quick auction because we have to be within the execution delay that we added. And we also have a smart contract implementation of commit and reveal auction to get a baseline. Now, the interesting magic trick is that our smart contract for the sealed bid auction on the Dawn style blockchain looks exactly like an open bid auction because it's really the system underneath that's doing all of the heavy lifting, and you have relatively simple logic at the end. Now, some results and discussions. First, we asked, did we achieve our security properties? We argue that we did because the causality is respected. The transactions are already ordered when they are revealed, so you can't go and alter the state. And we have fairness. We argue that we do because there's no way to cancel a transaction after it has been committed and revealed. So in terms of benchmarking, the threshold public key encryption requires 212 bytes net per transaction, and the amount of computation scales linearly with the number of transactions you put in. The threshold identity-based encryption, however, can be amortized a little bit because the multiple transactions can share a single decryption key. So you have upper bounds on the slides that tell you how much at the maximum you can get if you have one transaction per block. So to summarize this a bit in a table, we see that the performance for TIB is better, but the nice property of TPKE is that it's the inclusion of the transactions that triggers its decryption. So this is a bit safer if you have a transaction that doesn't make it into the blockchain. As a result, we think that TIB is great for auctions, because if you have a late bid, it doesn't really matter. But the best use case for TPKE is front-running protection. Now, from the application's perspective, what's better, what's worse? Well, we've removed the capital inefficiency that we had in the ANS auction, but we currently consume twice the amount of gas compared to the commit and reveal auction, and we've increased the execution latency because of the delay. That's kind of an interesting point, because if you look at this from a theoretical perspective, if normally only transactions that are ordered by the consensus group should matter, applications outside of the blockchain should not make decisions based on something that is not final. But in practice, people will use a couple of transactions, especially in Ethereum, a couple of confirmations, sorry, and consider that a transaction has made it if it has a certain number of confirmations. So in practice, this adds delays, and this adds delays for applications. This also means that simulation, in order to decide the gas or to decide if the transaction is going to be successful, is harder because you have less information, less current information, and that you have to wait longer for execution receipts, which affects some programs like Foundry, for example. The other drawbacks of the Dawn architecture is that it will require a hard fork, as we've discussed. It also breaks EIP 1559, which is the base gas, the auction market for transactions reform, because it needs to know how much gas was in the previous block, and it's difficult to do that if you have delayed execution. And it breaks some other things, and it also loses us a lot of the benefits of MEV. You might think there are benefits to MEV, and yes, that is the case, because before proposers were simulating transactions and trying to extract the most amount of value using things like MEV boost, flashbots, and all of that. It was difficult to promptly liquidate a position on chain because you could not, the block producer could not arrange to do that. It's also harder to have well arbitraged pools because the proposer is not smart enough to do it, so the prices arguably were worse. And the chain had a lot of failed transactions that would just waste resources because you did not have revert protection with flashbots. Whereas since we have the MEV pipeline, we have some of these nice functionalities. Now, having said that, what future works can be done in this area of research? We make a couple proposals. So the first one is, can we reintroduce some of the MEV pipeline that we lost? Potentially, what we could do is have a fast lane section at the end of the block, where after the encrypted transactions have been executed, we can have a few MEV transactions to do liquidations and arbitrage, for example. Then can we show the contracts and the transactions themselves their decryption key? Why would you do that? There are two benefits. First of all, you could allow applications to block the fast lane and say, okay, you can't bid from the fast lane because otherwise it's cheating. And the second thing you get is you get synchronous randomness. This is a cryptographic property of the encryption schemes we use, which is also used by the DRAN project, which is that decryption keys can also function as random beacons. So it's not quite a first. I think some networks have synchronous randomness, but we can have synchronous randomness as a bonus on top of delayed execution. Now, can we encrypt more fields? Because in the prototype, we just encrypted the destination address and the data. The problem with that is you need to be able to know that there's a valid signature and that the account that sends a transaction has enough gas to pay for it. But the potential solution to that is you can use zero knowledge to prove that the transaction inside ciphertext is valid without actually revealing the entirety of it. So this leads to an interesting question. How does this impact censorship resistance? Let's say we have these almost completely encrypted transactions, and we have a centralized sequencer. Well, what the centralized sequencer can do is it can require people to prove more things, to prove that they are not on the blacklist. But it's interesting because anyone who transacts immediately knows what the transaction is. So you can have censored rollups, but that are transparent on their censorship. Now, whether that's desirable or not is up to the community to decide, of course. And finally, I would like to give some acknowledgement to some people who've been helpful in the project. And quickly conclude. So we have this implementation of delayed execution, which is a realistic demonstration, and we have a sealed bid auction that runs on it, which is cool. We think that delayed execution enables patterns that would not be practical otherwise. For example, the sealed bid auction, the simple sealed bid auctions. But there are some drawbacks when it comes to implementing, especially on existing chain. Two things that can help us would be abundant computation so that the gas is not that much of an issue, and fast finality so that the execution delay can be lowered. Now, that's it. I will link to you the full report from my thesis, and I am awaiting your questions.
Brilliant presentation. Do we have any questions in the audience today? Anyone? Yep, right over here. She has a mic here. You can speak into that so everyone can hear. Thank you.
This is here. Well, you can see me after or in the recording. Okay, there we go.
All right, great. Do we have any other questions from the audience today? Yep, right over here. Maybe throw the mic. Okay.
Thank you for your presentation. Really great stuff. Did you look at Shutter Network, which does threshold commit and reveal style encryption, and how does your system differ from that?
Yes, I've talked with people from Shutter Network and from Nethermind. The difference, at least currently, is that Shutter Network is trying to work without hard forking, is trying to do something very progressive to get to essentially the same point. Whereas in the project, we said, okay, we're going to need to hard fork, so we just we did something that's not backwards compatible at all, and try to get directly to the thing. But I think we will converge roughly on the same type of design.
Okay, brilliant. We have one more question over here.
So how big of a changes did you have to do to Ethereum, like this hard fork? Is it something that's has even a chance of getting into mainnet, or is purely research thing?
Yes and no. The code is not that complicated. The complicated thing is trying to make Ethereum agree to trust a threshold network to decrypt things in time. And there's a lot of this is not popular on the L1. They have a system where they want to have liveness, and this is the big potential issue with these types of systems. And also people who work on this on Shutter Network know this. So that's the L1 story.